Hey class, today we're going to be doing lesson 4.14, part 2 for AP Statistics. We're going to be talking about conditional probabilities today. So first, let's start with the definition. A conditional probability is based on a subset of the population or the sample. Therefore, the denominator of the conditional probability is equal to the size of the subset. So it's not going to be, our denominator isn't going to be the entire population or the entire sample size. It's going to be only a subset of that. All right, so let's look at this example. Every student at WHS was asked their grade and to identify the extracurricular activity in which they are most involved. So we have a nice table here with all the information, including the totals, which is really helpful. If you're given a table of information and it doesn't have the totals yet, what you're going to want to do before you do any of the probabilities is calculate all the totals of all the different categories. So on the bottom and on the side and the total. All right, so a non-conditional probability would be something like, find the probability a randomly selected student is a senior. So out of all the students, randomly select one, what's the probability that they are going to be a senior? And remember, in AP Stats, we want to write that probability statement. If you're missing that, you're going to be missing points. So out of all 1,600 students, how many are seniors? Well, the 12th grade seniors, there's 425 of them out of 1,600. Again, in AP Stats, you do not need to reduce the fraction. You don't need to give a decimal or a percentage. Unless it specifically says what's the percentage, then it's kind of nice to answer in a percentage. Now, a conditional probability would be something like, find the probability a randomly selected student is a senior given that he or she is most involved in fine arts. So that word given, and sometimes they use the word given and it's nice and obvious. Sometimes they don't, and we have to kind of just be really careful when we read. But if I'm given the information that the senior is most involved in fine arts, we know that is a fact, then I'm only going to use, and let me get my highlighter, I'm only going to use these numbers. I'm not going to use any of the other numbers. So at this point, I don't care about any of these numbers. I only care about the fine arts. And the way we write this, we write the probability of, and actually we'll go over notation in a second. If you forget the notation, you can just write it in words. So a senior, so what's the probability that we have a senior given that they are most involved in fine arts? So out of all the students that are most involved in fine arts, because I know that that is a fact, then how many are seniors? Well, we have 125 seniors out of 435 total students. All right, let me get rid of all that here. So that's kind of the basic definition of conditional probability. They'll tell you that we're only looking at one specific subset of the population or the sample, as opposed to looking at all of the people that are sampled. Now, why are the denominators above different? So the denominators change because the conditional probability pertained to only fine arts students, not the entire 1,600 students that were surveyed. Symbolically, the notation for conditional probability is the P parentheses A, a vertical line B, and try to make that vertical line kind of a little bit bigger than the others. That's what I like to do, so it doesn't look like a 1 or something weird. Event B is the condition, so the second one after that vertical line is a condition that occurs or exists before event A. Let's see, we've got the formula, and this is on the formula sheet, the probability of A given B, and that's how we read that, the probability of A given B equals the probability of A and B. Remember, that's the intersection of the two events. So in your table, that's the box where those two cross each other, divided by the probability of your condition, which is that second one in the probability of A given B. So the probability of B becomes our new denominator. By the way, note, it doesn't have to be A given B. It could be the probability of B given A. It would still have A and B on the top, that box where they overlap each other, but then our probability of A would be on the bottom because that would be our given condition. So this is on your formula sheet, so you don't have to memorize this one. Now, to finish this example here, use the data to compute the conditional probabilities. So the probability that a student is most involved in athletics given that they are a 10th grader. So we can do this a couple different ways. I know that our formula says the probability of divided by the probability of, and we could do that. So the probability that they are athletics and 10th grade divided by the probability that they're in 10th grade. So if we look at the probability that they're in athletics and 10th grade, so coming back up here, athletics and 10th grade is 160 out of 1600. 160 divided by 1600. And then the probability that they're in 10th grade is 390 out of 1600. 390 out of 1600. Now, dividing fractions, I keep the same one on the top the same, change it to multiplication, and flip the bottom one over. So if you notice, the 1600s cancel out, which means we didn't actually need to do it this way. I'll show you how to do it on the other one. So we could have just done 160 divided by 390, which is more like the example that we were looking at before now with the seniors given that they're most involved in fine arts. If I say, okay, out of all the 10th graders, so this is how I like to do it. Out of all the 10th graders, so just these ones, cover up all the other numbers, just look at the 10th graders, what's the probability that they're most involved in athletics? So given that they're 10th graders. So we've got that 160 out of 390. So it's another way, and I think it's a much easier way to calculate these probabilities. All right, so, and again, you don't have to simplify that or anything. You can leave it just like this. So let's just kind of skip to that easier way. We don't need to use the probabilities per se. We can just use the numbers in each category. So the probability that they are in 12th, given that they are in the other, and then remember this little C means not. So that's the complement of the other category, complement. So first, let's figure out how many are not in other. So come up here. Other has 565. So then other complement would be 1600 minus 565. Let me get my calculator for this. 1600 minus 565 is 1035. So the probability that they are not in the other category is 1035 out of 1600. So if we think about it this way, given that they are not in the other category, so they are either in fine arts or athletics. So I don't care about any of the other numbers. I'm only looking at those and that total between them. So the total between those two is that 1035. Now I want the probability that they're in 12th grade. So how many students, are in 12th grade given that they're not involved in other? So other complement. So that's going to be 275 out of 1035. 275 out of 1035. And I can just leave it like that. Now I kind of showed my work up in the table. I showed how I got that 1035, how I'm calculating that 275. So it's good to show your work. If you didn't do it up in the table, you could just kind of write it into your fraction and show your work that way. And I didn't write the probability statement because it's already written for me. So it's a little bit of a loophole, which is nice. If it's already on the paper, you don't have to repeat it. Okay, let's go to the next page. So we have the same category, the same data here. So just some probability review. Find the probability that we have junior. Well, this is not conditional. Juniors, we have 410 juniors out of 1,600 students. Juniors or athletics. Remember, juniors or athletics means that I want all the juniors, I want all the athletes, but I only want to count this one once. We have to be careful. So we could do 410 plus 600 minus 140, because in the 410 and the 600, we've counted that 140 twice, over 1,600. Or we could Well, I think that that's probably the easiest way to do this. We could just sit and add a bunch of stuff together too, but I think that this is the easiest using our formula. You do want to simplify this. So we get 870 over 1600. You could have added, let's see, or athletics. So this one, this one, this one, this one, and this one, and this one. If you added all those categories together, you would have also gotten the 870. So a couple of ways we can do that. Probability of junior and athletics, and so they have to be a junior, and it says where the event is randomly selecting a junior who is most involved in athletics. Now, this is not conditional. It's just saying I'm randomly selecting a junior who's involved in athletics. A junior involved in athletics, there's 140 of them out of the 1,600 students. Now, I'm going to give the decimal version of this because we're going to compare it to number 4. So this would be 0.088. Now, the second one, number 4, it looks like it is the exact same probability statement, but it's a different probability problem. So if they do this to you, they will explain it in words. So just read carefully. It says, find the probability of junior and athletics where the event is randomly selecting a junior and then randomly selecting a student most involved in athletics, assuming the events are independent. So you have 2 students here. Here, you only had 1 student. So read carefully. If they don't give you this information, then I guess you can just assume that it's just 1 student. They'll usually give you some information. All right, so if they're independent, then the probability of A and B equals the probability of A times the probability, I ran out of room. Probability of A and B equals the probability of A times the probability of B. So if they're independent, and they told us that it's okay to assume it. So I'm going to want the probability that the student is a junior. So the first student selecting a junior and then selecting someone that's involved in athletics. So the probability that someone is a junior is 410 over 1600 times the probability that they're involved in athletics. There's 600 of those students out of 1600. So again, pulling that from my table, and I get 0.096. So again, I'm just using this 410 for my first one, 600 for the second one. I know that technically, and we'll talk a little bit about this, technically, if I choose 1 student who's a junior, and then I'm choosing a second student, that second probability is going to be a little less because I have 1 less junior, which means I could have 1 less students in athletics, depending on who I chose. And so the events aren't exactly independent, but it did tell us we're allowed to assume it. We can also assume independence using the 10% rule in AP Stats. Let me write this somewhere. I don't know. Here, let me write it at the top. So just a quick note, the 10% rule states that if your sample size is less than 10% of the population, you can use or assume independence. So in this case, I'm selecting 2 students out of 1,600 students. Is 2 less than 10% of 1,600? Absolutely it is. So then I can just use independence. It may not be independent, but if your sample size is less than 10% of your population, the math is going to be so similar, your answer is going to be so similar that it really doesn't matter if you assume independence or not. So just kind of a nice little shortcut. All right, now let's look at some conditional statements. So the probability that we have a junior given that they were in athletics. So out of all the students in athletics, there were 600 of them. How many were juniors? 140. Now the other direction, what's the probability? So this was the given condition. This was the condition, so that's the one that goes in the denominator. So now we're saying, what's the probability that if I select a student, they're going to be most involved in athletics, given that I'm only looking at juniors? Well, there are how many juniors? There are 410 juniors, and 140 of those are most involved in athletics. So again, if I just look at this category and I cover up the rest of the numbers and I don't even look at them, Out of 410, there's 140 that are most involved in athletics. And the difference in context, so just contextually, because obviously these are going to be, this one ends up being, let's see, 140 divided by 600 is 0.233, and 140 divided by 410 is 0.341. You don't have to get the decimals, but I want you to see that these are definitely different numbers. The numerator is the same, but the denominators are going to be different. So in context, the probability of junior, given that they're in athletics, is choosing a junior from the subset of athletics. So only looking at the subset athletics and choosing a junior from there. Probability of athletics, given that they're junior, is choosing an athlete from the subset of juniors. All right, next page. So suppose the probability of A is 0.8, probability of B is 0.65, and the probability of A and B, so remember this is the intersection, and I keep saying intersection because I want you to really connect that to the point of your table where they intersect each other. Or in our Venn diagram, if I have an A and a B, then they intersect 65% of the time. So 65% are involved in A and B. Now, we went over these tables in the last lesson, so if you didn't watch that one, make sure to go back and watch that video. So here, I don't have any context, so I'm just going to have A or not A, B, not B. And let's see, I've got 65% in A and B. Probability of A is 0.8, probability of B is 0.65. Ooh, interesting. So if the probability of B is 0.65 and the probability of B and A together is 0.65, then B and not A doesn't happen. So this is a little interesting. That sometimes happens in our probability. But let's fill in the rest of this. So 0.8 minus 0.65 is 0.15. So here's my 15%. And then to get to 1, I have a 0.2 on the bottom. So all the probability that A doesn't happen. Probability of B not happening is 35%, which makes this a 0.2 or a 0.20 there. So outside of our Venn diagram, we want a 0.2 showing that when neither of them happen, it's 20% of the time. You don't have to make both diagrams. I usually go with the table. Just make the one that's more helpful for you. So the probability of A given B. So the probability of A and B divided by the probability of B. So A and B. So think about it this way, kind of like the other ones. If I want to only look at B, I'm just going to look at these numbers here. So given that B has happened, I'm not going to look at any of the other numbers on the table. What's the probability of getting A and B? Well, we have 0.65 out of 0.65, so it's actually 100%, which is a little strange. Sometimes that happens. The probability of B and A, or sorry, B given A. So the probability of A and B on the top still, or B and A, same thing. But now it's divided by the probability of A. So for this one, I would only look at these numbers. I'm not going to look at any of the other numbers on the table. So out of only A, so 80% on the bottom, out of all 80% of those, what's the probability of getting B? Well, we'd have 0.65 out of 0.8. Now, I don't like to leave decimals inside fractions. It's not quite as nice. So let's just make that one decimal here. So divide the two, I should get 0.813, round to 3 decimals in AP Stats. It's required. All right, A and not B. So this is just straight from our table. A and not B, or B complement, is going to be 0.15. A given not B, or A given B complement, is going to be, so again, thinking about our highlighting here. So given the condition that we have B complement, so not B. So out of just those numbers, A happens 0.15 out of 0.35. So we get 0.429. All right, let's look at the next example. Of the 100 movies reviewed by People Magazine and USA Today, People gave a must-see rating to 25. USA Today gave a must-see rating to 40, and 15 were given a must-see rating by both publications. Given that a movie, there's that word, given that a movie was rated a must-see by People. So there's our conditional statement. And I'm going to highlight that. Given. Okay, what is the probability that it also received a must-see by USA Today? So I would strongly suggest that you make a table or a Venn diagram if you prefer. I like tables a little bit better. So I'm going to make a table. I'm going to have, let's see, People and USA. So USA, let's do People. People must see, and People not must see, I guess. Not see. You don't have to see it. And then we have USA must see and USA not see. Okay, so now let's see. Let's put these pieces in here. So 100 movies total. So I'm going to put 100 down here. USA or People gave a must-see rating to 25. So People said 25 of them were must-see. So that goes outside of our table. USA said that you must see 40 movies. 15 were given a must-see by both. So now I can piece together the rest of this puzzle. 15 plus 10 is 25. 15 plus 25 is 40. I need a 60 and a 75 here to add to 100, which makes this one 50. So now let's write our probability statement. So given that it was a People must see, what's the probability that it was also a USA must see? So if I'm only looking at the ones where People said it was a must see, so just that column, what's the probability? So out of 25 movies, what's the probability that USA also said it was a must-see? We get 15 out of 25, which is 0.6 or 60%. All right, given that a movie was not rated must-see by People. So now, given that People said you didn't have to see it, what's the probability that it also did not receive a must-see by USA Today? So USA not see. So now my given condition was that People said it was a not see. And if the highlighting helps, I really would suggest using it. So get a highlighter or just use your hands to cover up the rest of the numbers so that you don't see them when you're doing these problems. So out of 75, USA said that you don't have to see 50 of them. So that's going to be 0.667. All right. Last page, let's talk about independence. So this is a little tricky, and I know students struggle with this one a little bit. So really watch this video, really try to understand it. Ask me questions in class tomorrow if you need to. If event A and event B are independent, then the probability of A given B is the same as the probability of A. Similarly, so just note probability of B given A would be the probability of B. So this is the definition of independence, and I'm going to talk about this for a little bit, so really listen. Assuming B has already happened, what's the probability that A is going to happen? Well, if that's the same as A happening on its own, then B happening had no effect on the probability of A. That's the definition of independence. Two events are independent if one of them happening has no effect on the probability of the other. So if B already happened, then what's the probability that A happens? Well, if that equals the probability of A all on its own, then B had no effect on A. So this is the definition of independence. There are other formulas you can use to show independence, but I really like using this one because it shows that conceptual understanding of independence. Let's look at an example. A lending institution issues both adjustable rate and fixed rate mortgages on residential properties classified into 3 categories. We have single family home, condominiums, and townhouses. The probability distribution displays the bank's long run lending data. So anytime it says make a probability distribution, they want you to make one of these probability tables. Now, before we do anything, this one didn't give me the totals. So like I said earlier in the video, I want you to find the totals. So the total across would be 0.70, 0.30. You can just add them, 0.50, 0.30, 0.20, and then make sure that that adds to 1. Add them down, add them across. Make sure you didn't miss anything. Determine if the events adjustable rate mortgage and condominium are independent. So if they're independent, then the probability that you get an adjustable rate mortgage, given that you purchased a condo, would be the same as getting an adjustable rate mortgage, regardless of whether you got a condo or not. So finding this probability of adjustable rate given that they were in a condo. So out of 30% for the condo, adjustable rates were 21. Does that equal, adjustable rate mortgages, which was 0.70 out of 1.0? Well, do the math. So does 0.21 divided by 0.3 equal 0.70? Yes, it does. 0.70 equals 0.70. Check. The adjustable rate mortgage and condo are independent. So given that they had a condo, the probability that they got an adjustable rate mortgage was 70%. Well, the probability that they get an adjustable rate mortgage total is 70%. So condo has no effect. Buying a condo had no effect on the probability that they would get an adjustable rate mortgage. So that's independent. Determine if adjustable rate mortgage and townhouse are independent. So let's do this again. Adjustable rate mortgage, given that they were in a townhouse, is that the same as adjustable rate mortgage on its own? So out of all the townhouses, we had 0.20. Out of all of those, we had 9.09 adjustable rates. Is that the same as 0.70? Well, 0.09 over 0.2 is 0.45. That does not equal 0.70. So now if they bought a townhouse, that changed the probability that they would get an adjustable rate mortgage. So it changed the probability. They're not independent. And townhouse are not independent. Okay, I would suggest you try the next problem on your own. So pause the video. I know this video is getting a little long, but it's a really important lesson. Pause the video, see if you can make your own probability distribution, and then work through this problem on your own. That's our last example. So probability distribution, police report that 78% of drivers stopped for suspicion of driving under the influence are given a breath test. So we have, breath test, no breath test, and then we have a blood test and no blood test. 78% are given a breath test, 36% are given a blood test, 0.36. 22 are given both tests, 22%. So let's see, this is going to make 0.56 and 0.14, and I need 64 to make 100. I need 22 to make 100, and that leaves this with 0.08. Are the events mutually exclusive? Let's talk again, review mutually exclusivity or mutual exclusivity. So DIY, so are the events giving a DUI suspect a blood test and a breath test mutually exclusive? So mutually exclusive, if they were mutually exclusive, it means that they wouldn't overlap at all. So no, we don't even have to do any work here. So they are not mutually exclusive since 22% of the drivers who were stopped were subjected to both tests. If they were mutually exclusive, it would have been 0% had both tests. Now, are they independent? So now I want to figure out, come back. The probability that they were given a blood test, given that they had a breath test, is that the same as the probability that they had a blood test overall? So out of all the breath tests, so 0.78, what's the probability that they had a blood test? It was 0.22. Does that equal, question mark, probability that they had a blood test was 0.36. So take 0.22 divided by 0.78. I know I'm kind of running into the bottom of my page. 0.282 does not equal 0.36. So they are not independent since these things did not equal each other. All right, and that's it for today's lesson.